Today we're going to be talking about dynamic programming. And to understand dynamic programming, let's start at the motivation behind it. So let's start with Fibonacci. So we start with Fibonacci. The Fibonacci follows this sort of sequence. So we go 0 plus 1 is equal to 1. We're going to take these last two entries and add them together. So then we're going to get 1 plus 1 is equal to 2. And we're going to get 1, take these two entries, 1 plus 2 is equal to 3. Take these two entries, then we're going to get 2 plus 3 is equal to 5. Now, if we were to draw this in a recursive tree, we're going to have two options. We're going to either take this left path here. Let me try to retry that. We're going to take this left path here. We're going to take this right path here. So that is to either you can go left or right. And to go left is to take n minus 1. So this is n minus 1. This entry right here, n minus 1. And in recursion, we're going to keep hitting this left case before we can resolve this right case. So we're going to keep going 3, 2. Now when n up here is, so this n right here, when that is equal to 2, it's going to call this again. And then it's finally going to hit n is equal to 1. And if n is less than or equal to 1, we are going to return n. So in this case, we're probably going to hit a 1 here. 1's going to return, and now 2 is going to have this 1. Now we can finally, since this has finally been executed, we now can perform this right tree. So we're going to perform this right tree, which is this minus 2. Which is going to give us 0. So we're going to get 0 on this right path. Then we're going to return the 0. And now we're going to finally get our first entry, which is this 1 plus 0, this 1 plus 0 entry. And this is going to be stored in our 3. Now, if we were to keep doing this, we're going to get minus 2, so that would be 1. We'd get 1 in this case. Then we go up and go to the right. We're going to do minus 2. Minus 2, that's going to be 2 here. And then we're going to go up again. We're going to finally hit this. We're going to hit this 3 case. We're going to do 5 minus 2. We're going to get this 3. And we're going to repeat this subtree over here on the left. And you can see that we're repeating 2. We've already done the 2 calculation. We've already done this 3 subtree calculation. Memoization is strictly the practice of saving previous computations. That is it. So memoization, and so let me write that out. Memoization. So we're going to use memoization. Memoization. We're going to save these entries. And by saving these entries, by saving 2, we're going to save 2. And 2 returns 1. This 3 call here, over here, we're probably going to get, so this is going to be 1. We're going to get a 1 from this. And this 1 is going to return just another 1, so we're probably going to get 2 here. And then so on and so on and then so on. So the next time we hit this 3, we can skip having to run these left and right calls, and simply call our memoization table here, so sort of like a memory, this memoization table, and return this instead of having to compute these bottom left 2 entries once more. Now, the act of sort of committing or producing or incurring memoization, saving previous entries, and building up towards our final solution is called dynamic programming. It is the act of using memoization to solve your problem. This on its own, we see that, let me erase some of this. On its own, we see that the Fibonacci sequence, since we have two recursive calls happening, we're going to get this runtime. We're going to get big O of 2 to the n, because we're making 2 recursive calls, which both are going to take about n time. So we're going to get 2 to the n. Now, since we save these recursive calls, we only really need to make these calls, these entries, we can save up time and see that we're only ever doing n calls. We only need the first n calls to predict the rest of our tree. So this new thing we're getting here, let me cross this out with red, this new call that we're getting that we really want to use is going to be n this big O of n. We want to get a big O of n because we only need the first n computations for the rest of our tree. That is the basics of dynamic programming. Now, in dynamic programming, we can get rid of a lot of overhead. Now we're going to be talking about the bottom-up approach. So the bottom-up approach. Let me draw the call tree again. See, on the right here, we have 5, 4, so this is our call tree that we're getting here. 1, 2, 3, 2, and 1. And you know our base case is here, where we get the 1 and the 0. And we see that if we're going to perform this using standalone recursion, where the computer is keeping track of what function calls that we're making. So this is the stack. Our computer is keeping track of this. Let me write this out, the stack. So we have the stack here. And it's keeping track, our computer, as we go down in this tree. So we're going to hit this first left call, these first left calls. We're going to get 5 is on the stack, 4 is on the stack, 3, 2, and then 1. And then we're going to pop down over and over again. So let me just do 1. Let me do 1 here. So we're going to get 1. We finish, we return this call. So we pop it off the stack. Then we're going to get 2. And then 2 is finally going to be able, since we just popped off this left entry here, which returned 1, we can finally evaluate the second half. And then we can throw onto the stack, 0, which is going to return 0. And that's how we get this 1 plus 0 here. So it's going to return that. And we see that this makes us go all the way down. We have to first go all the way down, and then we have to go all the way back up. Instead, if we know that we're just going to go all the way back up, why not start at the bottom? This is called the bottom-up approach, where we know we have to start with these base case solutions. And if we just need these, why don't we start with these, then work our way up? Since these are not needed at all, since these entries are not needed at all, we only really need to compute these entries here. So how can we do that? Let's try this out. Let's make this function we have here on the left, this recursion function, into a bottom-up approach. So now let's examine this. Let's state our base cases. We talked about having 1 and 0 here. So let's start out with our base cases. Let's just draw this out. So we have 1. Let's have it right here. We have 0, and 1. Let's draw this in a one-dimensional table right here. 0 and 1. We know to get the next entry, we need to compute these two to get this entry right here. Let's label these. So this would be index 0, index 1, and index 2. This tells us that we have to start our algorithm at index 2. We have to start at index 2 because the algorithm really starts with these base cases, and we can't compute anything before these. So we must start with these to begin our bottom-up approach. So we start with 2, and then as the algorithm says, we're going to need, let's denote it F. Let's denote it F here. We're going to need the entries F. Let's say we start at I, so we're at I here. We're going to need I, so 0 plus 1 here, so these is entries 0 and 1. We're going to need I minus 2, because this is 2 spaces to the left of I. We're going to need I minus 2 plus F I minus 1. See, because this entry right here is 1 to the left. And we see that what we wrote down here, is very much the same as our recursive statement up here. It's just that instead we're using tables instead of recursion. So we can keep building this up from the bottom and start, and we see we have 0 plus 1, so that's going to be 1. Then we're going to take our next entry. Let's go up to 5 here. It's 4 and 5. Let's just go up to 5, and maybe you can guess what these next entries are going to look like. And so take these next 2 entries again. Take these next 2 entries again. We're going to get 2. Take these next 2 entries. We're going to get 3. Take these next 2 entries, and we're going to get 5. So this is the bottom-up approach, where instead of going all the way down and then coming all the way back up, we can just start at the bottom and make our way up to our final solution. So how do we start this? How do we make this function up here into a bottom-up approach? So we're going to say fib. We're going to start out the same way. Then we're going to diverge using our table implementation. So before, recall that we said that we had some table F, and we started with these entries 0 and 1. When making these bottom-up approaches, you really have to identify what are your base cases. We got a hint over here somewhat. You can look at this and you can say, okay, we at most go n-2, and we at most go n-1. So I know that my table is going to be at least n-2 deep, or two extra entries in our overall table. So we're going to have these 2 extra entries. We're going to start with these, and then we're going to have, so these indexes, so 0, 1, 2, and we're going to start at 2 for our algorithm. We're going to start at 2 and build our way up. So let's start this. So we have our n entries that we're going in. We say, okay, calculate this n. We're going to start off with our base case. We're going to say, we're going to give this table f. We're going to give this f variable a table. So this arrow is going to denote that f is getting a table. And then we're going to start out with our base cases. We're going to say f0 is going to get 0. And we're going to say f1 is going to get this 1. Now this is going to again be the 0, 1 entries for our tables, so it's important to establish the base cases for what you are going to be working with. Then this next thing that we're going to do here is our for loop, because there's no need to have a stack anymore using a table. So there's no reason to have a stack going all the way up and all the way up and all the way back down. We're just working our way up linearly through this one-dimensional table. So we're going to start with this for loop, and we're going to say we're going to start with I is equal to 2. So we're going to start our for loop at this 2 entry, so we can kick off this n-1 and this n-2 calculation. And I'm going to denote this here. I'm going to denote this long arrow to be, we're going to run this for loop all the way until n. So this is going to be our for loop here. So we start at 2, and then we're going to increment by 1. So we're going to increment by 1 all the way up. So that's going to be implicit all the way up until n. So now the magic happens in this next entry. So now we start with entry 2. So we're going to calculate entry I here. And this entry I here is going to be equivalent, is going to equal f I minus 1 plus f I minus 2. Now notice this is strikingly similar to our original recursive statement. Instead, we're just using a table to build up our solution from the bottom up. So we're going to now, when we're done with this for loop, we're going to return the last entry. And the last entry should have our final calculation. So we're going to return fn. And then that is how you solve it in a bottom-up method, so a bottom-up solution. Now, what is the runtime of this? We see that our only for loop here, so let me try to make this a lot neater. So we see that our only for loop here is n. So as our inputs grow to infinity, we can see that our runtime is going to be big O of n. Now let's start with our first problem, subset sum. So our first problem is going to be subset sum. This is given a set of integers. Say we had the set of integers. So if I were to write this out, we would have 3, 6, 1, 7, 2. So given these, and a target sum of 9. So we have our target sum is equal to 9. Find the max subset P of S such that P is less than or equal to T. So P in this case, so is subset P of S. So S is referring to this set right here, the set of numbers 3, 6, 1, 7, 2. And our target weight T is this 9 here. And you want to find a subset P, so a subset of S, such that we can create some sort of amalgamation, some sort of set containing some number of elements such that the numbers added together are less than or equal to t. So we can take 6 and, let's say 6 and 2, 6 and 2, that's 8, so that would be equal to 6 plus 2 is equal to 8. This is still less than or equal to t, which is equal to 9. So we're still falling into that category, and this problem is asking what subset, so what arrangement of elements from S can we get such that the sum is less than or equal to t. That is the max sort of P that we can get, the maximum subset that we can get. So this is the problem statement. Let's go on to how do we solve this problem. Now let's work through solving this problem. We have the subset 3. We started with 3, 6, 1, 7, 2. We have to work through this manually before we can think about solving this in an algorithmic way, before we can abstract it. So we have a target weight 9. We have 3, 6, 1, 9, 7, 2. And now if, let's say, we had some solution set n, so let's write n over here, so n is our solution set. Say we had some sort of solution set over here, and we just perchance chose 3 to be in our solution set. We chose 3 to be in our solution set, so the next set that we have here is 6, 1, 7, 2. And now let's add that to our solution set. Now, what would we make the new t here? So this 9 is equal to t, our target weight. Since we've taken out 3, if we were to say t is 9, that wouldn't really reflect that we chose 3 to be included in our answer. We aren't asking, is 6, 1, 7, 2 less than or equal to 9 here? We're not asking that because we've already included, since we've already included 3 here in our solution set, we need to reflect this in our weight. This wouldn't be really asking the same question. So here, to reflect that we just took 3 out in our target weight, we can now decrement our target weight to 6. So taking the 3 from this 9 here, we get a new target weight 6. Now we can continue to operate on this problem. We can either choose to take this 6, or we can skip and take 1. Say we skipped and took 1. This would be 6. This would be 6, 7, 2. And the solution set would contain 3 and 1. So we know we can either 1 take, or we can either 2 skip. And if we take, we know that we need to decrement the target weight, And if we skip, it doesn't really matter if the target weight is staying the same. So the target weight stays the same. So let's just stay the same. Stay t. Let's just keep that t. So we can either skip or take. In this case, we took here, kind of skipped the step where we skipped. So if we were to draw that intermediary step where we skipped it, let's say we just chose to skip it, and our thought of recursion, so 6, 1, 7, 2, we're sort of being redundant here. We still have, instead of looking at 6, we're looking at 1 here. And we still have the same sort of 6 we have going on here. Now, in this solution here, we took out the 1, so it's going to be 5. The target weight is going to be 5. So we know that we can either skip or take, and if we take, we decrement the t. Now, this is the problems or subcases that we're going to either have that either take or skip. We can draw this in a recursive relation. Say we had our function, it's optimal choice. Say we had optimal t. Let's give ourselves a lot of space here. So say we had this optimal solution, and this optimal solution took in I, because we have to keep track of which place we were looking at. So we're now writing out these subcases that we need to look at, which are going to help us. What do we need to keep track in this recursive relation. So our optimal solution, or our optimal function here, is going to keep track of I as we're going down in the recursive tree. And then what else do we want to keep track of? We want to keep track of the position I, but we also want to keep track of the t, that we know we're decrementing the t over and over again to find this optimal solution. So we're going to include the t here in our solution. Now, what do we want to find? We want to find the max. But let's first think about our base cases. What is our base case? When do we stop? Well, we stop when we have nothing to look at. This means that the target weight must be t is less than or equal to 0, that t must be equal to 0 at this juncture if there's nothing there. So if t is equal to 0, or if you want to be more specific, you could say less than or equal to, just return 0. As there's nothing that we can sum here, so the best that we can do, or we can return, is 0. This next step is sort of what is another base case that we can have, that if we are looking at, say, 7 here, we're looking at 7, but if we choose 7, if we choose this I, so this is I right now, if we choose I, this is going to be greater than, if we add I, this is going to be greater than our sum or total that we have. Our target weight is 5 here. 7 is greater than 5. We can't, that's impossible to take that solution. That's impossible to take that solution. So let's say if the set that we're looking at here, the set is S, so that when Si is greater than t, so if we're taking 7 here, and if 7 is greater than 5, let's just skip it. What does that look like? If we were to skip this, we would say OPT I minus 1. Say we were looking at this in descending order, and it's sort of going back in sort of I's to mimic, to set up for our bottom-up approach, or our recursive mimicking. Let's say that I minus 1, so to move to the next one, and we're going to keep the target t, that we're going to keep t here. So this is skipping. This is what happens when we skip. Now, our last choice is our max. We want to find the maximum solution of something. Now, in our max solution, we have two choices that we can either skip, so we have the skip solution. Here are our choices. The two choices that we make every time we're evaluating this array. That we can either do the OPT, the optimal, we can do I minus 1, t, or so is in the recursive tree of picking this option of skipping, are we going to find a better solution? Is this going to return a high number from the recursive tree of choosing this left side, or this left side, or we can go to the right? Are we going to get a better solution, a higher solution, if we were to take this I? So this means that we took this I, so we're still going to decrement to look at the next. We're still going to, if we take 7 here, or take 2, we still have to decrement our sort of I that we're looking at. The target weight is going to be subtracted by the weight that we just took, And now, how do we keep track of that we took a certain item? That when this item returns, that we're returning this sum that we're accumulating over time. To add this sum, we're going to add it near the end. I'm just going to write it in a different color to make it stand out. That we're going to add this optimal solution. So we are going to decrement. We are going to look at this next item. We're also going to add the SI that we were just looking at. So we can think of this as our next step, that we're going to skip and look at the next solution that we could possibly get, or we can call this our build solution. Our build solution that we did choose this I, and we're going to build on top of it by adding or summing the answer that we are collecting, and we are going to keep track of certain things that are changing throughout our algorithm. Now, I'm going to clean this up and have this on the next slide, and we can start building an algorithm that uses this recurrence relation. Now, before we can write the algorithm, we're going to have to understand how this is being built up in the table. Before with Fibonacci, we saw that we had a one-dimensional table, as we only really needed to keep track of this one I as it built up with our bottom-up solution. Now, going straight for this bottom-up solution that we're going to do, we're going to have to understand how the table is being built up. Since we have two variables to keep track of, this is going to incur a two-dimensional table. Our two-dimensional table is going to have T for columns. It's going to have I for the rows. Now, this is going to start, we're going to use our example. So we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And to start off, we're going to start off with the null subset or null set. Then we're going to excuse the brackets and just do 2. Then we're going to have 2, 7. Then we're going to have 2, 7, 1, 2, 7, 1, 6. Then 2, 7, 1, 6, 3. Now, this first entry is going to be 0. Because with a target weight of 0 and a subset of null, the best we can do is 0. And then if we continue on this row, if we have nothing within our sort of set that's null, we're going to see that we're going to keep getting 0. So this is going to be the base case for the sets. And then we see that if we have a subset of 0, the best we can do is 0. So this is also going to be a base case. Now, let's start out with this 2. Examining 2, if we were to start with 1 with a target weight of 1, the best we can do is 0. With 2, we can do 2. And since we can only pick 2, the best we can do throughout is 2. Now, if we have 7, we're now examining 7. We're not examining 2 anymore. We're on the position I where we're examining 7. So if we start out with 0, we have 0. The best we can do is pick 2. We can also now pick 7 just by itself. Then the best we can do is 7. Then the best we can do here is 9. Now, if we do 1, 7, 2, 1, 7, 2, we're examining 1 now, but we're still looking at all combinations. So the best we can do now is 1, starting out with a target weight of 1. Then we can do 2. Now we can have 1 plus 2, so we have 3. And the best we can do here is 3, 3, and 3 up until we get to 7. And then we have 1 plus 7, so we have 8, and then we have 9. Now we have 6 into the mix, so we put in 1 here, we still have 2, 3, we can only do like 1 plus 7 or 1 plus 2, so we're still having the same thing, so we're going to have the best we can do here is 3, best we can do here is 3, and we can just do 6 by itself, then 7, 8, then 9. Now, try to get this last row. What can we get for this last row here? Okay, now let's try it. 1, we can get 2, we can get 3, of course. Now we can do 1 plus 3, which gives us 4. We can do 2 plus 3, which gives us 5. And then what we had before, 6, 7, 8, and 9. Now, building this up, we see that our best solution here is 9. Now, that's how we build up our solution. Now, let's talk about something called backtracking. What did we pick to get to our solution? So this is called backtracking. What did we pick to get here? So examining this next and build solution, we only picked if our value increased. If we skipped, nothing changed about this t value. So let's check that. So we look at this value and we see that, okay, it's not any bigger than the value we chose previously. So it seems like we skipped it. Oh, this value is the first value we picked. This was the value when we were examining 7. So 7 must be in our solution set. So now when we picked the build solution, we decreased the t. So now let's decrease the t by 7. So 1, 2, 3, 4, 5, 6, 7. We examine 2, and is 2 greater than the next solution? It is, because it means that we didn't skip it, so it means that we picked it. This 7, 2 is our solution. Let's go ahead and write algorithms for this. Now let's begin with the algorithm definition for our bottom-up solution. So we know that this bottom-up solution is going to take some S set and a target weight T. And we know that in the bottom-up solution that we're going to start with our base case, then build up. So what are our base cases again? Recall that in our table, our base cases is when T was 0, and we had the empty set. When the set was empty, no matter what column we had, it was always going to be 0, as that's the best we can do with an empty set. If the column was 0, the best we could do with any row is also 0. So these are the base cases that we're going to start with. Another clear indicator of how deep our base cases need to go is that we see that we only ever go deep as 1. We only dig as deep as 1. So we know that we can start off with one iteration later than we need. So what does that mean? What does that mean? Let's start with our base cases. So we have, let's say for M, standing for memoization table, M gets a 2-dimensional array. Now, for the base cases, we saw that for any row, so this is row, so the 0 row, for any row, it doesn't matter what any column, so I'm putting a star for the column, no matter what column you had, it was always 0. Now, vice versa, if M, so for any row, if we had column 0, doesn't matter what row you were on, it was still 0. Now, we know we need combinations. We know for Fibonacci we used one for loop. But to get the combinations of everything this direction, so everything in our table, we're going to use a nested for loop. So let's start out with the first for loop. So we're going to have for I is equal to 1. We're 0 indexing this, so our base cases are 0, so we're going to start at 1. So for I is equal to 1 all the way up until the length of S. Let's use the same colors here, the length of S. So here's the length of S. And the next for loop is going to be for t, so little t. For little t is equal to 1 all the way up until big T. So this is going to be an iteration that's doing 0, 1, 2, 3, and so on, all the way up until t. This is how we're going to get both our combinations. So we're going to get both our combinations. Now we want to encode this first argument here, where if Si is greater than t, we just want to skip. What does skipping mean? It means that we're just going to take the same entry behind us. So let's write this out. Let's use a different color. So if Si, recall that S is some array and we're indexing it with I. So that's what I means here. So if Si is greater than our little t, so for this iteration, this t, then we want to, for this iteration, so Mi little t gets, so this is going to be equal to M, so we're going to copy this statement up here, Mi minus 1 t. So we're just going to make it the same as the last iteration. So we're starting from our base case, it's still going to be 0 if the next sort of S that's coming in, if the next weight that's coming in is greater than the target weight that we have now. Else after that, we can just encode the last condition, because that's the only thing we need to account for, so this last condition. So we set for this iteration I, so an Mi t, this is going to be equal to, so we're just going to encode this, the max, so max, we're just going to write down the statement, so it's Mi minus 1 t versus not M, we had S here, so we're going to put S. So S I plus m I minus 1, and in this case we have the little t minus s I. Now this is going to give us, hey, is the last solution bigger, or can I get a bigger solution with this weight plus the last solution? That tells us that we actually took the last solution. So after this whole for loop runs, we can just return m. We can just return m and begin our backtracking. Now let's begin the definition for the backtracking. So let's just say back, and the backtracking is sort of just going to get the memoization table that we had before. Perhaps we're going to be using the same. We're using s, and we're going to need t here. We're going to need t. Now, to backtrack, we're just going to follow our logic backwards. As before, we showed that we start at the bottom right row, and following the logic, what can we do? So if this selection up here is greater, so if we saw that the next row is greater, that means we picked something. If it's the same, that means we skipped some sort of solution. So we always know when the rows change in this particular problem that we picked the solution that we wanted. So let's try to encode this. So we're going to start at the top or the bottom right and make our way back down. So that means that we're going to have t and I again. So t, let's have our little t. This is going to be set. This is going to be set to t. And our s, or sort of the I here in this case, the I, is going to be set to the length of s. So these are the possible or last cases that we can start with. And we're going to make our way all the way back down to 0 to follow what we picked along the way. So that means we're going to have a while loop. So we're going to have while I greater than 0 and t is greater than 0. Perform these actions. So we're going to keep decrementing I and t based on the logic that we have. So we're going to examine these two blocks of logic that we have. And we can see that, okay, when do we actually pick s? So when the next row, so when the row above us, so if we have rows here, if we think about m, this is the row, and this is the column here. When the row, so when I minus 1 is different than the current, so when I minus 1 is less than the current sort of row, then we know we picked an s here. So let's write this logic. So if this current iteration, so m, I, t, mit, if this is greater than m, I minus 1, t, we know we selected this build solution. So if that's the case, that means that this current solution is part of our solution. So let's create another variable called, let's just call it sol for solution, and we can give this in a little empty array, and we can say that the solution, we can add to the solution, so solution.add, we're going to add this current I, so I. So we used this I in our solution. Now, since we picked this, we have to follow what we chose. So we chose I minus 1 and t minus the s that we just chose. So maybe for clarity, instead of just putting I, we can immediately put s, si. We chose si. And we can decrement our I. Our I is going to be equal to, what do we put here? I minus 1, so I minus 1. And then our t here, so our little t is going to be equal to t minus the s I that we just picked. Else, so we want to also take care of this else statement. So if we didn't pick this solution, else, what does that mean? That means we skipped. And that means I, so let's try to keep it consistent, that means I is equal to I minus 1. And then after this while loop keeps going, at the end of this, we will have our final answer. So return S, our solution, return solution. So together, these are what those two algorithms are. So let's evaluate the runtime for both of these. Again, we have this for loop here and this for loop here for our building up or bottom-up solution. You see that we have a nested for loop. So whatever S is and whatever T is going to be our runtime. So big O, let's say N is in terms of the length of S. So we can just say N. So N is equal to the length of S, how many items we have in our array. And let's just put T. So NT for T being the target weight. So here we're going to incur big O of NT as our worst case time scenario. And for our backtracking, we're only going down I times. So if we look at T, every time we decrement I, we also decrement T. And we see that we follow, in decrementing I and T, we follow this zigzag pattern. That when we hit the null statement, we're also hitting the null T. So in all, we're actually just running for big O of N. Big O of N, where N is the length of the array. So that's the runtime for both of these. Now let's talk about Knapsack, which is an extension of the subset sum problem. It starts out the same. We have a set S with n items, each with a weight W, but now each weight or item is associated with a value. And we have a knapsack, or what we can totally get altogether. So our target weight is capacity W. And again, we are finding P, a subset P of S, such that the sum of all the weights, so the sum of the weights of the items that we collected, is under our target weight. And the sum, or the values of P added together, is the highest possible value that we can achieve. Looking here on the right, we can see an instance of a knapsack. So altogether, you can sort of think of this as if we are a burglar and we have, our knapsack right here. If we are at a museum and the museum has such and so items, and each item has a weight to them, what is the subset or the set of items that our knapsack can carry that we can take home and have the highest achievable value? So that's altogether what this problem is trying to say. Now, I'd like you to pause and try to figure out what the subcases for this problem is. So if we were to write the OPT again, so if we write the OPT, and what would we give it for values? And what would be the cases? Pause the video and try to see what that is. Now, if you saw the pattern, if you saw the trick, this is strikingly similar to our last problem, the subset sum, where we want to keep track of I and a target weight, in this case W. We'll still have that same base case where when W is equal to 0, we just want to return 0. Or when the target weight coming in, so when Wi is greater than W, we want to skip. So what does skipping look like again? We just move on to the next entry, so OPT, and we say I minus 1, and we keep W the same. And then what do you think this last entry is here? So we're going to still need that max. But what is this max? What does it contain? It will ask, I'll keep this all in white. So it'll ask, we can either skip, so is the bigger solution the next solution? So I minus 1, W, or is the bigger solution when we take this item I, when we take this item I, what are we keeping track of? What's the value we want to get bigger or incur over time or add or sum? It's the value. The value is what we're trying to capture. So here we're going to say VI plus OPT I minus 1, where we are now evaluating the next item, and we have to keep track of the weight. So say if we took S, no, not S here, 6 here, if we took this 6, this item 2, we're going to have to keep track of the weight. So the weight here is going to be W minus WI. And it's basically strikingly similar to the last problem, just with VI swapped out and some of the variables swapping out looking different. So now let's try and code this up. So now let's try to create this definition. I encourage you to try it on your own to see how well you can do. This is similar to the last step problem. So we know we're going to get some set S and a target weight W. Now, how are we going to encode this VI and WI behavior? We could, for the data structure of S, receive it as some sort of, as S could be an array, and that array could have multiple arrays indexed 1, 2, 3, and so on, where each array could be indexed 1, 2, and the first item in each array is the value, and the second item in that array is the weight for that specific I element of S. So let's write this as a comment so it's clear to the audience what we are trying to write in our pseudocode. So we're going to say that SI is going to be the index, and SI0 is going to be the value, and that SI1 is going to be the weight. Now, let's state our base cases because we are working with the bottom-up solution. So let's start from the bottom and let's identify those base cases again. Similar to the subset problem, we're going to start with a 2D array because we are working with 2 items and we know the base cases. So we're going to know it's a 2D array, and for the base cases, if the row is 0, doesn't matter what the column is, it's going to be 0. So on, that if doesn't matter what row we are on, if the column is 0, we're always going to get 0. Now let's try these combinations again. Since we're doing I and W, let's make a nested for loop. So for I is equal to 1, this is 0 index, so we're skipping this 0 entry here. So when I is equal to 1, going all the way up until the length of S. So let's use the same colors here, the length of S. And for the W combinations, we're going to use for little w. So for little w is equal to 1 all the way up until big W, which refers to this big W up here, the actual weight we got into our function. We are going to try to encode this first argument here. So when WI, so when the specific weight of the ith item is greater than the wth iteration that we are on now, we're going to skip. So we're just going to skip. We're not going to actually take it. So let's encode this behavior. If, so we're going to say S, when SI1, so we're getting the weight, is greater than the little w that we have, little w, then we're going to set for this iteration. So for this iteration, m, it's going to be w, so little w, is going to be equal to mi minus 1, little w. Now else, we can now do the next or last, the else, the bottom statement. So for this current iteration, the w is equal to the max. So what is the better solution? Is it going to be the last solution or the next solution, which is going to be mi minus 1 w, or is the bigger solution we're going to have to encode our value. So our value is SI0 plus, what are we going to do here? This is going to be mi minus 1 And what do we have here? So W minus WI, so the specific W. So it's going to be little w minus SI 1. That is going to be, kind of ran out of a little bit of space there. Let me try to move it to the left. Then after that, we can just return. So let me write that out here. So we can return M. So we can start our backtracking. So now let's work on the definition for our backtracking. I encourage you to try this on your own, as it's going to be very similar to what we did last time. So now we're going to receive our M, and let's say we got our S and our target weight big W, and now we are going to start from the end and make our way all the way to the back from our bottom up to figure out what we just picked. So we're going to set I that we had before, and now I is going to be going to get the S, so the length of S, and our little w, so little w is going to get our big W, so we're going to start with our largest weight and make our way all the way back down to the base case to figure out what we picked along the way. So now we're going to start with our while loop, so we're going to have while I is greater than 0, and little w is greater than 0, we're going to begin our backtracking. Now, looking at our logic again, we can do this a couple of different ways, but how do we sort of check when we picked this build solution? So we know we picked the build solution when our value actually changes in the table because we are adding values. So all we have to check here is the current solution that we're working on, is the one we're working on bigger than the row below, So let's do this. Let's encode this behavior. So our first if statement is going to be if this iteration that we're on, so this iteration that we're on, if this cell that we are on, so IW, is greater than the row above us, so I minus 1 W. This is true. That means we did our build solution. So if we did our build solution, let's add another variable called solution. Let's give this just an empty array. And now let's add this to our solution. So add, let's just give it I, because there's a lot of variables that come with the S here. So we're just going to give it I. And now, so we know we took that I, and what do we do when we take? So we decrement I, and we decrement W. So we're going to see here that I is going to equal to I minus 1, and that W is going to be equal to W minus S I 1. Recall that this is how we, in the previous problem, indexed our weights. Now, the next, or else, the else statement, so this means if we did not pick our build solution, what else happened? So that means else we didn't pick anything, so we're just going to decrement I. So I is equal to I minus 1. By the end of this, we can return the solution. We can return solution. And that is the backtracking. For the final problem, we're going to be doing unbounded knapsack. And again, it's the same setup as the bounded knapsack all the way through. But the last line is that there are an infinite number of copies of each item. So we could keep taking the same item over and over and over again, or we can decide to go to the next item. Now, how does this OPT going to work out? We can still write our, we know we're going to have our general cases here, where if it's 0, if W is equal to 0, then we're just going to return 0. Or we can have our skip condition, or OPT, we can just do I minus 1. We have the skip condition, when WI, the incoming weight, is greater than the weight that we can accessibly use right now. And what would be this max? How can we how can we incur multiple takes of each copy? Well, we could start writing it out. Let's do max. We can find the max of, let's use a different color. We can find the max of the OPT, so we can have our skip condition. The OPT I minus 1, W, and then what could we do here? Well, let's say if we could do, maybe if we had some sort of iteration J times the value of I, and plus the OPT. We could do something like that, you know, have some iteration. If we do times VI, we would have to multiply that again with the weight. So that would be W, so the weight minus the J times WI. And this max would have to have some sort of iteration on it, maybe from J equals 1 to infinity, something like that, where we would have to iterate over and over again, multiplying Ji on the value and the weight. Well, we can do one thing better than this, because if we were to have a nested for loop that's dependent on weight, you know, the only time this would break out is if this weight, if these two conditions either met. So the worst we could have is we have our NW, but we're going to have another for loop measuring how much we can take for this weight. So say if the weight was maybe 1, or the value was 1, we could just keep doing W and have another nested for loop of W, which would make us have NW squared. Now, if we want a for loop, there's a more clever way of doing this, where instead of having another for loop, we can make the recursive function itself perform an iteration. So how can we do that? So if we want to iterate over the same item, we can do something like this. We can have Vj, the same setup, plus, now this is where the magic happens, where instead of decrementing I, we keep I the same. We keep I the same, and then we can decrement W as normal by the Wi. Here, we're going to iterate over the same item, and the same conditions will apply. We can do this without having that nested for loop. Now, let's write this out more cleanly and begin the algorithm. So let's start this definition, and as always, I encourage you to try this on your own. So we know that our optimal solution is going to take, again, some S, and we're going to take in the W. Now, to start writing this, we know our base cases. So again, let's just write out our base cases. We have M here. So M is going to get some to the array. And again, doesn't matter if it is doesn't matter what row we're on. If the column is 0, it's going to be 0. And it doesn't matter which row, if the row is 0, it doesn't matter which column you're on, it is going to be 0. So it's going to be 0. Now, we can start our for loop again. So we're going to have our for loop. So we're going to have for I is equal to 1 going to the length of S. So the length of S here. And then the inner for loop, which is going to be for our little w is equal to 1 all the way up until big W. And we're going to run our first condition here. As always, we're trying to encode this. So we're going to say if, let's say if Wi is greater than W. So if remember how we encoded this, so if to get our weight, so if the weights, so on this index on 1, so this is just getting our weight here, little w, bigger than little w, then we, for this current entry, so for this current entry, Wi, little w is going to be equal to the last entry, so Wi minus 1, w. Now let's write our else condition, so we're going to have our else condition, and now we're going to encode the last statement. So this last statement here is saying sort of the max, so we're saying for this current, for this current condition, or this current cell, so mi little w, we might run out of space here, so I'm just going to preemptively move this back a little bit. Now this is going to be equal to, so we're going to write the max, so max, so that's max, poorly written though, but so that's the max, and it's going to be the optimal solution, so it's going to be m, so the skip condition, I minus 1, w, or is s I 0 plus m I, so this current, so we're on this current solution here, so we're iterating over and over and over again, I, and we're going to do w minus si 1 brackets, and return m. So this is how we are going to be working through this solution. Now notice how this is probably going to affect our table. Since we're not decrementing I here, we could have some solution, say starting here, and if we chose to keep this entry, if we chose to keep iterating over this entry, I is not going to update, so we're going to stay on the same row, and we're going to move up by the weight, and we could just keep moving up by the weight up until w, but then we'll stop. Then we'll stop because we've hit the max weight that we can get. Or let's say we're starting here and we decide to move to the next row and start taking an item. Say we don't decide to take that item, so we move to the next row, and now we say let's keep taking this item. So to take this item, we move the weight, and we say, well, I don't want to take any more of this item. We move to the next row. I want to take more of this item, more of this item, more of this item, and so on. So we're going to be iterating over the columns and iterating over the rows. So we're going to have this pattern here, and we're going to see that the I and the W are going to matter in our backtracking. And this is going to change the runtime overall, since we're iterating both column-wise and row-wise. Let's go ahead and try the backtracking solution. So as always, I encourage you to try this again on your own, and let's begin. So we have the subset S that we're bringing in, the weight W, and the M memoization table. With our backtracking again, we are working from our final solution all the way back up to the base case to figure out what we picked along the way. So we're going to start at the top, so that means we're going to give I is going to get the length of S, and then our little w is going to get w to set us back at the end of the column to work our way to the base case, and then we are going to get our solution, and our solution is going to be an empty array to begin with. Now we're going to get our while loop, and we're going to say, well, I is greater than 0 and little w is greater than 0. We're going to perform some actions. Now you could start trying to attack this v here, this value, and start trying to evaluate if our build condition has happened. Or we can do it the other way around. We could start evaluating our skip condition, because our skip condition here is saying that we are on some row, that we were doing some adding on one item, but we decide to skip here, which means we go to the next row. So this means that the above row must be the same as the below row. So we can check this condition instead, because if it's not our skip condition, it must be our build condition. So let's go ahead and try this. So we're going to say if mi, so the thing that we're working on now, is equal to mi minus 1 w, and we're just going to set I is going to be minus 1. That's all it's going to be, because that is our skip condition. Else, this must be our build condition. So this means that we're going to add this to our solution. So solution dot add s I, and then we are going to decrease, because if it's not our build condition, the only thing we do here is decrease w. So if we're staying to the notation that we've been using before with indexing the weight, we're going to say the weight, these little w, is going to get little w minus s I1, which is indexing the weight. And by the end of this, we should have a full solution set, and we can return m. So examining both these algorithms side by side, we see that the bottom-up solution, that we only had a nested for loop here, so that's just going to be thinking about n in terms of the elements in S. That would be nw. Then for the backtracking solution, that would be, since we were looking at our memoization table, that we could iterate over columns when we were checking to see the same row, and we can iterate over rows when we decided to skip. This is going to incur that we can iterate over all rows and all columns, which means that we are doing n plus w, which is different than the previous solutions, as when we decreased or skipped the rows, we were decreasing w as well, so w was not iterating. But in this case, we have that we are iterating over columns as well. That is the end of this video. If you enjoyed it, don't forget to like and subscribe. For code implementations on all of these algorithms, in the description below, there is a repository. In the implementation section for Python, there are implementations of all of these algorithms. These videos are more up to date, so if you see that in the textbook that is also linked with the implementations that there are any discrepancies, you may issue a pull request or post a GitHub issue. And with that, thank you.